In this video here, we're going to take a look at some quantitative examples of melting and perhaps some crystallization examples in a binary phase diagram. Now, this is a diagram from the online textbook by Dexter Perkins, and it shows phaolite versus forsterite with a compositional axis here on the bottom, and a temperature axis, temperature increasing towards the top. And we have the melting of forsterite at 1890 degrees centigrade and pure phaolite melting at 1205. That intersection there of this melting loop happens just above that 1200 degree hash mark. In between, we have this melting interval as we explain in another video. So what about the case of, let's say, something that is 80% phaolite? So if we have something that is 80% phaolite, what would it look like in terms of its melting behavior? Well, it's not going to have a sharp melting point. I'll try to draw a vertical line, not perfectly vertical, but probably close enough for our purposes. And it's going to hit the solidus here at a temperature of a little below, well, somewhere between 1200 and 1300 degrees centigrade. So there's the 1300 degrees centigrade hash mark there. The first liquid that will be created, we can find by drawing a horizontal line from the bulk composition here. This is what we started with. That's our bulk composition. So we take a mineral that has this composition. But when we start melting it, the liquid, that's not a perfectly horizontal line, we'll probably intersect around here. The liquid that's going to be created is going to be much richer in phaolite. And I'll try to draw a vertical line that would reach this point here. This is the composition of the liquid. So this would be, if we're looking at the fraction of phaolite, we started with 80% phaolite in our original mineral, but here the composition of that liquid, I'll just draw a superscript L, is going to be something close to, it looks like about 95 weight percent phaolite. So the liquid is much, much richer in iron, and this is at the heart of the idea of planetary differentiation, or the differentiation of igneous rocks. We can create liquids that have different compositions than the solid materials that we start out with. Now, what if we continue heating? So if we heat this fellow just to the point where it hits the solidus, then we're going to create an infinitesimal amount of liquid that will have this composition here. At what point will it be fully melted? Well, it'll be fully melted. Let's continue our vertical line up when this bulk composition reaches the liquidus. So we go from here. We have solids from this temperature all the way up to here. And then between the solidus and liquidus, we have a mixture of solid plus liquid. And then everything above the liquidus will all be liquid. So we can think of this as being contoured from 0% liquid at the solidus to 100% liquid here up at the liquidus. Well, what would happen if we continue adding heat to the system? Well, if we create liquids that are more iron rich, then what we've done is we've subtracted out some iron from the solid. That'll actually force the solids that are left over to move in the more magnesium-rich direction. So if we add heat and increase temperature, we move upwards. As we do so, we're going to pull out iron that'll force the solids in this direction to the right. And the sum of those two vectors is the liquidus curve. So the next little bit of material that we'll look at, we'll say, is at this temperature here. So after we've pulled some iron out of the solids, the new solid compositions, the new crystal compositions might be here, and then the new liquid compositions will be here. Notice that these new liquids are still much more iron rich than the solids that they're in equilibrium with, but they are more magnesium rich than the liquids that we started out with. We have a more magnesium rich solid, so it gives us a more magnesium rich liquid. But the liquids are still very different. The liquids are moving in a more magnesium-rich direction as we move upwards in temperature. The sum of those two vectors gives us this liquidus curve. So the liquids will migrate up this curve just as the solids migrate upwards on this curve. And then when the liquids finally reach this point here, then the liquids will have the same composition as the solids that we started with. In the case of equilibrium melting, where we let crystals plus liquids sit around and equilibrate with each other, then those crystals and liquids will be able to exchange iron magnesium components. And if we let that happen, then the case for the liquid being equal to the bulk composition will also be the case when we have 100% liquid. So our liquids will not get past this point. We can't, by the time we add enough heat to get the liquids up to this point here, we've run out of solids. What are the last solids that are left? If we ever want to know what crystal would be matched with what liquid, I'm using XTL as an abbreviation for crystal, we can just draw a horizontal line. The very last crystals that we would have would be something close to, it looks like about 30% phthalate. So we started out with something that was 80% phthalate. We drew off a lot of the iron to create liquids that follow the liquidus curve in this direction. As we pull out those iron-rich liquids, the solids move up this curve. And the last liquid that we have, when we finally reach 100% melting, will be at this composition here. And the very last little bit of crystal that'll be melted to produce that liquid will have this composition here. So long as we have the system that is in equilibrium, where crystals and liquids are always exchanging iron and magnesium components, then that's as much fractionation as we can get. We cannot get solids that are any more magnesium rich, nor can we get liquids that are any more magnesium rich. If we allow fractional melting to occur, in fractional melting, we take the tiniest little bit of liquid and allow it to be removed whenever we create a little bit of liquid. Then we can overshoot this boundary both on the solid and the liquid side, but that's probably better saved for another video.